Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be tackling a practice problem set that relates to our lecture on thermodynamics. Let's go ahead and get started with problem number 1. Problem number 1 says, if an object with an initial temperature of 300 Kelvin increases its temperature by 1 degree Celsius every minute, by how many degrees Fahrenheit will its temperature have increased in 10 minutes? Now, the first thing we need to understand to solve this problem is the relationship between temperature scales. First, the Kelvin unit and the Celsius degree, they are the same size. So a change of 1 Kelvin is equal to a change of 1 degree Celsius. Second, the Celsius and the Fahrenheit temperature scales, they're related by this equation right here. The temperature in Fahrenheit is equal to 9/5 multiplied by the temperature in Celsius plus 32. Now for this problem, we're actually interested in the change in temperature rather than the absolute temperature. Therefore, we only need the conversion factor for temperature differences, which is given by this equation right here. This says that the change in temperature in Fahrenheit is equal to 9/5 multiplied by the change in temperature in Celsius. Now, the problem states that the temperature increases by 1 degree Celsius every minute for a total of 10 minutes. So that means that the total increase in temperature in Celsius is going to be 10 degrees Celsius. We could take this value and plug it into our expression to get 9/5 multiplied by 10. Now 5 and 10 here are both divisible by 5. So if we divide both values by 5, we get 1 and 2 here. And what we're left with is 9/1, which is just 9, multiplied by 2. That gets us 18. That means that the increase in temperature in Fahrenheit after 10 minutes is 18 degrees Fahrenheit. Therefore, the correct answer for problem 1 is answer choice C. Fantastic. Let's do problem 2 next. Problem 2 says, which of the following choices correctly identifies the following 3 heat transfer processes? Statement 1 says, heat transferred from the sun to the earth. Statement 2 says, a metal spoon heating up when placed in a pot of hot soup. And statement 3 says, a rising plume of smoke from a fire. Now, for the first statement, heat transferred from the sun to the earth. The heat transfer from the sun to the earth occurs through radiation. Radiation involves the transfer of energy through electromagnetic waves, such as visible light or infrared radiation. This process does not require a medium, and it can occur through the vacuum of space. The sun emits electromagnetic waves that travel through space and reach the earth, warming its surface. Therefore, the correct identification for this process is radiation. What about statement 2? Statement 2 says, a metal spoon heating up when placed in a pot of hot soup. This illustrates conduction. Conduction is the transfer of heat through direct contact between molecules in a solid, liquid, or gas. When a metal spoon is placed in hot soup, heat transfers from the soup, which is the hotter object, to the spoon, which is the cooler object, through direct molecular interactions. Now, metal is a good conductor, meaning that it allows heat to pass through it easily, causing the spoon to heat up as a result of this direct contact. Thus, the process described here is conduction. What about statement 3? A rising plume of smoke from a fire. This illustrates convection. Convection is the transfer of heat through the movement of fluids such as liquid and gases. In this case, the fire heats the air around it, causing the air to become less dense and rise. And as the hot air rises, it carries smoke particles upward with it. This movement of heated air and smoke is a characteristic of convective heat transfer. So the correct identification for statement 3 is going to be convection. That means we're looking for an answer choice that says radiation, conduction, and convection in that order for statement 1, 2, and 3 respectively. And that's going to be answer choice A. So the correct answer for problem 2 is A. Let's attempt problem 3 next. Problem 3 says a 20-meter steel rod at 10 degrees Celsius is dangling from the edge of a building and is 2.5 centimeters from the ground. If the rod is heated to 110 degrees Celsius, will the rod touch the ground? And here we're given the coefficient of linear expansion for our steel rod. It's equal to 1.1 times 10 to the negative 5 inverse Kelvin. Now, when an object is heated, it expands, and the change in length of an object due to a change in temperature, it can be calculated using the linear expansion formula, which says that the change in length is equal to the coefficient of linear expansion multiplied by the original length multiplied by the change in temperature. Now we're given all of these values. Alpha is equal to 1.1 times 10 to the negative 5 inverse Kelvin. Our original length is 20 meters. And we're given the initial and final temperature so we can calculate delta T. Now our linear expansion coefficient, it's in units of inverse Kelvin. So we want our delta T to be in units of Kelvin so that Kelvin cancels out and we get our final answer in units of meter. But just like we discussed in lecture, we don't need to convert our temperature in Celsius to Kelvin because the Kelvin unit and the Celsius degree are the same size. And when our goal is to calculate change in temperature, it doesn't matter if it's in Celsius or if it's in Kelvin. The change in T is going to be the same. Let me show you. 110 degrees Celsius minus 10 degrees Celsius is equal to 100 degrees Celsius. That's our delta T. Now you will notice that if I convert these to Kelvin and take the difference, I will also get 100 as the difference. 110 degrees Celsius is equal to 383 Kelvin, and 10 degrees Celsius is equal to 283 Kelvin. And when I take the difference between these two, I get a difference of 100. So notice, you do not need to waste your time during the MCAT converting between Celsius and Kelvin when your goal is to calculate delta T. Just take the difference between the two temperatures you're given, whether it be Celsius or Kelvin, and just know that they are equivalent in both units. Again, because the Kelvin unit and the Celsius degree are the same size. So now that we know that, we can go ahead and start to plug values into our equation. We have 1.1 times 10 to the negative 5 inverse Kelvin. This is multiplied by our original length of 20 meters, and our delta T, which is 100 Kelvin. Notice that the Kelvin units cancel out. We're going to get our final answer in units of meters. Now, to do this calculation a little bit easier, I'm going to approximate this to 1. So what we have here is essentially 1 times 10 to the negative 5 multiplied by 20 multiplied by 100. 20 multiplied by 100, this is equal to 2,000. 2,000 multiplied by 10 to the negative 5 is 2,000 times 10 to the negative 5, which we can rewrite as 2.0 times 10 to the negative 2 meters, which, by the way, is also equivalent to 2 centimeters. So our answer is approximately 2 centimeters. And the answer choice that best aligns with this is going to be answer choice C. No, because it only expands by 2.2 centimeters. That's the closest value out of our answer choices to the number that we approximated, which is 2 centimeters. And so, if this rod is heated to 110 degrees Celsius, the rod will not touch the ground because it only expands by 2.2 centimeters, whereas the steel rod is dangling 2.5 centimeters from the ground. So it is off by approximately 0.3 centimeters. Again, the correct answer for 3 is going to be C. Let's do problem 4. Problem 4 says, what is the final temperature of a 3 kilogram raw iron fireplace tool that is left in front of an electric heater absorbing heat energy at a rate of 100 watts for 10 minutes? Assume the tool is initially at 20 degrees Celsius and that the specific heat of the iron is 500 joules per kilogram times Kelvin. Now the formula that relates the heat absorbed or released by an object to its temperature change is Q equals mc delta T, where Q is the heat energy absorbed or released in joules, m is the mass of the object in kilograms, C is the specific heat capacity of the material in joules per kilogram per degree Kelvin, and delta T is the change in temperature. Our goal for this problem is to calculate the delta T. And in order to do that, we want to isolate that variable. So delta T is going to be equal to Q over mc. Now we have the mass and we have the specific heat capacity, but we're not directly given the heat energy absorbed or released. But we can actually calculate it from the information we're given about the power. Now, the heat energy absorbed by the tool, it can be calculated using the power of the heater and the time for which it operates. Power is defined as the rate at which energy is transferred, and it's related to energy and time through this equation. P, power, is equal to energy divided by time. We're given the information regarding power and time, so we can solve for the energy by rearranging this equation. Energy is equal to power multiplied by time. Now, the power of the heater is given as 100 watts, and the time is given as 10 minutes. Now, here's something that sometimes trips students up. We need to convert this 10 minutes into seconds because the power is in watts and 1 watt is equal to 1 joule per second. So let's write that down. The power is 100 watts. Watts are equal to 1 joule per second. So our time cannot be in 10 minutes. It needs to be in seconds. 10 minutes, each minute is 60 seconds. This gives us a total of 600 seconds. So we are going to be multiplying 100 watts by 600 seconds. 1 times 6 is equal to 6, and then we have 1, 2, 3, 4 zeros to add. 1, 2, 3, 4 zeros. So the energy here is 60,000 joules. Now we have a value we can plug in for Q. We're given the mass, we're given the specific heat capacity. We can easily calculate this. Delta T is equal to 60,000 joules divided by the mass, which is equal to 3 kilograms, multiplied by the specific heat capacity, which is equal to 500 joules per kilogram per Kelvin. Now, let's multiply the denominator. 3 times 500, that's equal to 1,500. So what we have is 60,000 divided by 1,500. We can go ahead and cancel out some of these zeros. What we're left with is 600 divided by 15. This is equal to 40. The change in temperature is equal to 40 Kelvin, which, by the way, is equivalent to 40 degrees Celsius. That's our change in temperature. Now, Do not confuse this as the final temperature. Our final temperature is going to be our initial temperature, which is 20 degrees Celsius, plus however much the temperature changes by, which is 40 degrees Celsius. And that gets us a final temperature of 60 degrees Celsius, which means that the correct answer for problem 4 is going to be answer choice C. Awesome. Let's tackle problem 5 next. Problem 5 says, how much heat is required to completely melt a pair of gold earrings weighing 500 grams, given that their temperature is 25 degrees Celsius? Further, the melting point of gold is 1064 degrees Celsius. Its heat of fusion is 6.37 times 10 to the 4 joules per kilogram, and its specific heat is 126 joules per kilogram per Kelvin. Now, in order to figure out what equations we need to use to solve this problem, the first thing we want to do is we want to draw our heating curve for this specific purpose. We're starting off with solid gold earrings at 25 degrees Celsius. Then we're heating these gold earrings all the way up to their melting point at 1064 degrees Celsius. At the melting point, heat is going to be absorbed for the purpose of phase change. And this is where we're going to completely melt our solid gold earrings into liquid gold. So what we notice here is we have two different steps. The first step is going to require us to calculate the heat required to raise the temperature to the melting point. And the second step is going to involve us calculating the heat required to melt the gold. Now, for this first step, this first portion right here, we're going to be using our equation mc delta T. Here, m is the mass of the substance, c is the specific heat capacity, and delta T is the change in temperature. We're given all of the information we need to calculate the heat required for this segment. Our mass is equal to 500 grams. Now we want this to be in kilograms because our specific heat has units of joules per kilogram per Kelvin. So we want our units to match up so they properly cancel out. 500 grams is just equal to 0.5 kilograms. I got that by dividing 500 by 1,000. We can also go ahead and calculate our change in temperature because we know our initial and final temperature. Our final temperature is 1064 degrees Celsius. Our initial temperature is 25 degrees Celsius. This gives us a difference of 1039 degrees Celsius. Now we want our delta T to be in units of Kelvin because again, our specific heat is in units of joules per kilogram per Kelvin. The nice thing about calculating delta T is that it's going to be the same for the difference between two temperatures in Celsius as it would be if we were to convert them to Kelvin and then take the difference. So this 1039 degrees Celsius difference is also equal to 1039 Kelvin. If you're to convert these to Kelvin and take the difference, you would also get a difference of 1039. Now that we have these variables, let's go ahead and plug them in. Our mass is 0.5 kilograms. Our specific heat capacity is 126 joules per kilogram per Kelvin. And our change in temperature is 1039 Kelvin. Now, to make this calculation a little bit easier, what I'm going to do is I'm going to approximate this to 1,000. So what we have here is 0.5 times 126 times 1,000. I'm going to do this multiplication first. 0.5 times 126. This is essentially multiplying 126 by 1/2. We're going to get 63, and then we'll multiply 63 by 1,000. We're going to get 63,000 joules, which we can convert to kilojoules. That's going to be equal to 63 kilojoules. So that is the heat required to raise the temperature to the melting point. What about the heat required to melt the gold? So we want to calculate the heat for this segment now. To do that, we're going to be using our equation Q is equal to mL. Here, M is the mass of the substance, L is our latent heat. Here it's going to be that heat of fusion that we're given, which is equal to 6.37 times 10 to the 4 joules per kilogram. So we're going to put in our mass in units of kilograms so that it cancels out appropriately. That's 0.5 kilograms multiplied by 6.37 times 10 to the 4 joules per kilogram. Now I'm going to round this to 6.4 because that's an easy value to multiply by 0.5. That gives us 3.2, and then we want to not forget that times 10 to the 4 joules. Kilograms cancel out, so our final answer is just in units of joules. Now we can convert this to kilojoules as well. It's going to be equal to 32 kilojoules. So now we can add 32 kilojoules plus 63 kilojoules to get approximately 90 kilojoules. Now the answer that's closest to this value is going to be answer choice D, 97 kilojoules. And so that's how we answer this problem. We drew the heating curve, we calculated the heat required for each segment, the first segment where we increase the temperature to the melting point, and then the second segment where we are calculating the heat required for that phase change, and then we added those two values up to calculate the total heat required. Now, of course, we made some approximations to make the math a little bit easier without a calculator, and we got a close enough value to the real answer that it was easy to distinguish what our correct answer for this problem is. So again, the correct answer for problem 5 is D. Let's answer problem 6 next. Problem 6 says, given the cycles shown, what is the total work done by the gas during the cycle? Now, the work done by a gas in a thermodynamic process, it's represented by the area enclosed by the cycle on a pressure volume diagram. And this is because the work done by a gas in a single process is given by the integral of pressure with respect to volume, which geometrically corresponds to the area under the curve. The total work done by the cycle we're given in this pressure volume diagram is going to be the sum of the work for segments A, B, and C, or in other words, the area within the cycle. Now, because the area bounded by segments A, B, and C is a triangle, we can use our equation for area of a triangle to calculate the work done in this cycle. Now, the area of a triangle is equal to 1/2 multiplied by base times height. The base for this cycle is going to be 5 cubic meters. The height is going to be 3 pascals. So we can go ahead and plug these values into our equation. We have 1/2 multiplied by 5 cubic meters multiplied by 3 pascals, and this gives us a work of 7.5 joules. So we were able to take our base of 5 cubic meters and a height of 3 pascals, and we used it to calculate the area of this cycle to be equal to 7.5 joules. Now, is this positive or negative work? Here's a quick hint. Whenever you're looking at a cycle drawn on your pressure volume diagram, clockwise loops tend to do positive work on the environment, while counterclockwise loops do negative work. Now, this is a clockwise loop, so our work is positive. And that means the correct answer for problem 6 is going to be C. The work done by the gas during the cycle is equal to positive 7.5 joules. Wonderful. Let's do problem 7. Problem 7 says, in an adiabatic compression process, the internal energy of the gas blank. Now, in order to solve this problem, we need to understand what happens to the internal energy of a gas during an adiabatic compression process and how it relates to the work done on the gas. So let's break this down step by step. The first thing we want to understand is what is an adiabatic process. An adiabatic process is one in which no heat is exchanged between the system and its surroundings. This means that all of the energy transferred to or from the gas comes in the form of work. So again, for an adiabatic process, heat is equal to 0. Now, how does this relate to the first law of thermodynamics? The first law of thermodynamics states that the change in internal energy is equal to the heat added to the system plus the work done on the system. In an adiabatic process, we just said that Q is equal to 0, so the equation simplifies to delta U is equal to W. So the change in our internal energy is simply due to work during an adiabatic process. Now, work is considered positive when work is done on the gas, meaning that the surroundings do work on the gas, compressing it. On the other hand, work is considered negative when the gas does work on the surroundings, such as during an expansion. In this problem, though, we specifically are told we have an adiabatic compression process. This means that the volume of the gas is decreasing and work is being done on the gas. And that means that work is going to be positive. Now, since change in internal energy for an adiabatic process is just equal to work, and work is positive, that means that the internal energy of the gas increases during the adiabatic compression process. In a gas, internal energy is closely related to the temperature. So if the internal energy increases, the temperature of the gas also increases. But that's not what the problem is asking. I just wanted to add that last tidbit in just for you to keep in mind. Ultimately, what we need to answer in this problem is what happens to the internal energy of the gas and why in relation to work. So in short, all of that information was to say that the internal energy increases during an adiabatic compression process because positive work is done on the gas during compression, increasing its internal energy. And that best aligns with option B. Again, the correct answer for problem 7 is going to be B. The internal energy of the gas increases because the work done on the gas is positive. Let's do problem 8. Problem 8 says the entropy of a system can blank. A says never decreases. B says decreases when the entropy of the surroundings increased by at least as much. C says decreases when the system is isolated and the process is irreversible. And D says decreases during an adiabatic reversible process. Now, entropy is a measure of the disorder or randomness of a system. And the second law of thermodynamics, it provides guidelines for how entropy changes in various scenarios. The second law of thermodynamics, it states that the total entropy of an isolated system can never decrease over time. In an isolated system, entropy either increases or remains constant in a reversible process. And this principle is important because it highlights the concept that natural processes tend to move towards a state of maximum entropy. So let's go ahead and work through each of these answer choices. Option A says never decreases. This is incorrect. While the entropy of an isolated system never decreases, the entropy of a non-isolated system, it can decrease if there is a corresponding increase in the entropy of the surroundings. Therefore, this option is too absolute and it really doesn't account for non-isolated systems. So it's not the correct answer. Option B says decreases when the entropy of the surroundings increased by at least as much. Now, this is the correct answer. In a closed or open system, the entropy of the system can decrease as long as there is an increase in the entropy of the surroundings that compensates for the decrease. This ensures that the total entropy of the universe, system plus surroundings, still increases or remains constant, and that is very much consistent with the second law of thermodynamics. So B is the correct answer, but we'll go through C and D as well. C says decreases when the system is isolated and the process is irreversible. This is incorrect. If a system is isolated, no energy or matter is exchanged with the surroundings. And according to the second law, the entropy of an isolated system never decreases. It can only stay the same or increase, especially in irreversible processes where entropy generally increases. So C is not the right answer. Option D says decreases during an adiabatic reversible process. Again, this is also incorrect. In a reversible adiabatic process, there's no exchange of heat, and for a reversible process, the change in entropy is zero. Hence, the entropy does not decrease in a reversible adiabatic process. It remains constant. So D is incorrect as well. And again, the correct answer for problem 8 is going to be option B. The entropy of a system can decrease when the entropy of the surroundings increased by at least as much. Moving on to problem 9. Problem 9 says, a student making a coffee cup calorimeter fails to use a second coffee cup and inadequately seals the lid. What was the student's initial goal, and what was the result of this mistake? A says the student was trying to create an isolated system, but created an open system instead. B says the student was trying to create an isolated system, but created a closed system instead. C says the student was trying to create a closed system, but created an open system instead. And D says the student was trying to create an open system, but created an isolated system instead. Now, calorimeters, these are our best approximations of isolated systems where neither energy nor matter is exchanged with the environment. By failing to use an insulating layer and failing to fully contain the system, now heat can be exchanged with the environment and matter may be dispersed, and this creates an open system instead. So the student was trying to create an isolated system, but because of their mistake, they created an open system instead, and that best aligns with answer choice A. Moving on to problem 10. Problem 10 says a certain substance has a specific heat of 1 joule per mole per Kelvin and a melting point of 350 Kelvin. If 1 mole of the substance is currently at a temperature of 349 Kelvin, how much energy must be added in order to melt it? Now, to find the amount of heat needed to bring the substance to its melting point, we can use the specific heat. To heat 1 mole of the substance 1 unit Kelvin, it would take 1 joule of heat. Then after the substance reaches its melting point at 350 Kelvin, additional heat is going to be needed to actually induce the phase change. Therefore, the total amount of heat required is going to be greater than 1 joule, and the correct answer for problem 10 is going to be A. Let's move on to problem 11. Problem 11 says which of the following is not a state function? Now, as a reminder, a state function is a property of a system that is determined solely by the current state of the system. It is independent of the process that's used to achieve that state. Examples of state functions include internal energy. It depends only on the state of the system, such as pressure, volume, and temperature, and not on how the system arrived at that state. Temperature is also a state function. It is a measure of the average kinetic energy of the particles in a system, and it depends only on the system's current state. And then entropy is another example of a state function. It is a measure of the disorder or randomness of a system, And again, it's determined solely by the state of the system. So looking at our options here, internal energy, heat, temperature, entropy, we're trying to choose the one that is not a state function. We just said internal energy is a state function, temperature is a state function, entropy is a state function. What is not a state function is heat. And actually, this allows us to discuss path functions. A path function depends on the specific transition process from one state to another. The value of a path function depends on the path taken and not just the initial and final states. And the classic examples of path functions are work and heat. And so here for this problem, which of the following is not a state function? That's going to be answer choice B. Heat is not a state function, it is a path function. Moving on to problem 12. This problem says, the figure shown depicts a thick metal container with two compartments. Compartment A is full of a hot gas, while compartment B is full of a cold gas. What is the primary mode of heat transfer in this system? In order to answer this problem, let's go over our three modes of heat transfer. First, we have conduction. This is the transfer of heat through direct contact between particles. Then we have convection. This is the transfer of heat by the movement of fluid, liquid or gas itself. And then we have radiation. This is the transfer of energy through electromagnetic waves. In this given problem, we have two compartments that are separated by a thick metal wall. So let's break this down. Compartment A has our hot gas, so it contains a gas at a higher temperature. And compartment B has our cold gas. This is the gas at a lower temperature. And then we have this metal wall that separates the two compartments. The question is asking for the primary mode of heat transfer through the metal wall. Now, given that the compartments are separated by a thick metal wall, conduction is the most likely mode of heat transfer. Heat will transfer through the metal wall from the hotter compartment to the cooler compartment by conduction. The molecules in the hot gas will transfer kinetic energy to the metal's wall's atoms, which will then transfer this energy through the wall to the cooler side, increasing the temperature of the cold gas. And so the correct answer here is going to be answer choice C. Now, as for convection, this cannot occur through the solid metal wall since it requires the movement of fluid itself. It's not radiation because while radiation can transfer heat through empty space, it is not the primary mode here because the metal wall will mainly conduct heat directly through molecular collisions rather than relying on radiation. And as for answer choice D, which says enthalpy, this term refers to the total heat content of a system, and it is not a mode of heat transfer. So again, the correct answer for problem 12 is going to be answer choice C. Problem 13 says substances A and B have the same freezing and boiling points. If solid samples of both substances are heated in the same exact way, substance A boils before substance B. Which of the following would not explain this phenomenon? Now, answer choice A says substance B has a higher specific heat. If substance B has a higher specific heat, it would take more energy to raise its temperature compared to substance A. This would mean substance B heats up more slowly, explaining why substance A reaches its boiling point first. This could explain what we observed, so it is not the correct answer for this question because we're trying to look for an explanation that is incorrect. A is a possible explanation. Option B says substance B has a higher heat of vaporization. Now, a higher heat of vaporization means it requires more energy to convert substance B from liquid to gas once it reaches the boiling point. This would delay the boiling process for substance B, allowing substance A to boil first. This also could explain the phenomenon, so it is not the correct answer for this question. Answer choice C says substance B has a higher heat of fusion. A higher heat of fusion means it takes more energy to convert substance B from solid to liquid at its melting point. This would cause substance B to remain a solid for a longer time and delay its heating process, making substance A boil first. This could explain what we observe, so it is not the correct answer for this question. Then answer choice D says substance B has a higher internal energy. The internal energy of a substance refers to the total energy contained within it, including the kinetic and potential energies of its particles. While higher internal energy might suggest higher molecular motion, it does not directly impact the rate at which the substance reaches its boiling point or its ease of phase change. It is not directly related to how quickly a substance reaches its boiling point or the energy required for phase transitions or phase changes like melting or vaporization. And so option D is the only explanation that does not work for what we observe, that does not explain this phenomenon. So the correct answer for problem 13 is going to be answer choice D. Moving on to problem 14. Problem 14 says, in experiment A student mixes ink with water and notices that the two liquids mix evenly. In experiment B, the student mixes oil with water. The liquids separate into two different layers. The entropy change is blank for experiment A and blank for experiment B. Now, when the ink randomly disperses throughout the water and it mixes evenly, then the final state is going to be more disordered than the initial state. So the entropy change of this system is positive for experiment A. When the oil and water are mixed, we notice that they separate from each other. And so the final state is just as ordered as the initial state because the oil and the water are still completely separate. So the entropy change is approximately 0 for experiment B. So we're looking for an answer choice that says entropy change is positive for experiment A and 0 for experiment B. And so the correct answer for problem 14 is answer choice B. Moving on to our last and final question. Problem 15 says, which of the following processes is least likely to be accompanied by a change in temperature? Let's work through each of our options, starting with option A. This one says the kinetic energy of a gas is increased through a chemical reaction. Now, the kinetic energy of gas molecules, this is directly related to their temperature. If the kinetic energy of the gas increases as a result of a chemical reaction, this would typically cause an increase in temperature because temperature is a measure of the average kinetic energy of particles. So this process would likely result in a temperature change. Option B says energy is transferred to a solid via electromagnetic waves. Electromagnetic waves, such as infrared radiation, they can transfer energy to a solid, increasing its thermal energy. This absorption of energy would cause the particles in the solid to vibrate more, leading to an increase in temperature. So this process would also likely result in a temperature change. Option C says a boiling liquid is heated on a hot plate. Now, when a liquid boils, it's undergoing a phase change from liquid to gas. During this phase change, the temperature of the liquid remains constant even though heat is continuously added. This is because the energy is used to break intermolecular bonds rather than increase the kinetic energy. Therefore, the liquid's temperature does not change as it continues to boil. And actually, this is the correct answer for problem 15. It's going to be C. This is the most likely process where temperature does not change despite the addition of energy. But let's go over option D anyway. Option D says a warm gas is mixed with a cold gas. Now, when a warm gas is mixed with a cold gas, the kinetic energy of the gas molecules will redistribute, leading to thermal equilibrium. The final temperature of the mixed gas will be somewhere between the initial temperatures of the two gases. And so there is going to be a change in temperature as the gases mix. So this process would definitely result in a temperature change as the gases reach thermal equilibrium. So out of these four options, the one that is least likely to be accompanied by a change in temperature is going to be answer choice C. And with that, we've completed this practice problem set. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.